Hello everyone, my name's Alistair and I work for Western Digital as part of the RISC-V software research team. And today I'm here to talk about the 32-bit RISC-V Glibc port, the current status, and why it has taken so long to get here. This is recorded on the 20th of August and hopefully will be presented on the 3rd of September. During the presentation, I should be available in the text chat to answer any questions, and at the end of the presentation, I'll call in to answer any questions over video as well. So today's talk is going to cover, first of all, what Glibc is and why it's important, then what the year 2038 problem is, and how this applies to RISC-V, especially RISC-V 32-bit. Then I'll talk about the status of 64-bit time T in Glibc, the status of the RISC-V 32-bit port, what needs to be done in the future, and the benefits that RISC-V has over other architectures. Finally, I'll wrap up with the lessons learned from the upstreaming experience, and then we'll end with questions. So, what is Glibc? Glibc provides the fundamental function calls in user space Linux applications. These are things like open, malloc, read, printf, things like that. It's very difficult to write a user space Linux application without using at least a libc, and Glibc is probably the most common, especially in desktop class systems. Glibc also is what's usually involved in doing the kernel syscalls for you. It's the thing that calls from the user space, where your application is, down into the kernel space. You can do this yourself, but Glibc kind of provides a nice wrapper for you, and most applications just use this and don't do any syscalls. Glibc currently has 64-bit RISC-V support upstream, but does not have 32-bit RISC-V support. So before we kind of go into that, I want to cover the year 2038 problem, or Y2083. So in January 2038, the Unix Epoch will overflow a 32-bit signed integer. So the Unix Epoch is what Unix systems use to keep count of time. It counts time since January the 1st, 1970, and it stores this value in a signed integer. On a 32-bit system, it's stored in a 32-bit signed integer, and on a 64-bit system, it's stored in a 64-bit signed integer. So like I just said, on the 19th of January 2038, this will overflow a 32-bit signed integer and wrap back around. And this is called the year 2038 problem. So who cares? Does this matter? You might be wondering, does anyone still use 32-bit systems today? And if so, will anyone still be using 32-bit systems in 18 years from now? And will this actually lead to failures, or will some clocks just have the wrong time? So I'll kind of go through those three questions. So does anyone still use 32-bit systems? Yes, people still do use them, especially in embedded applications. There are lots of 32-bit embedded Linux all over the place. And will anyone still use them in 18 years' time? So you might not expect your phone to last for 18 years, but some industrial use cases, it's definitely expected to last longer than that. Things like planes, trains, cars, spaceships, everything like that, you expect to last longer than 18 years. You don't want your car ABS to stop working just because it's the year 2038. And will this actually lead to failures? So yes, systems that use absolute time will fail, and systems using relative time will probably have bugs as well. There's lots of user space software that was written never expecting this to happen, and that probably will stop working. So there are lots of examples of this, and the Deep Impact Space Probe is probably one of the most famous ones. It was launched in 2005, and it tracked time as a 1/10 of a second increment since the year 2000. When NASA lost contact with it, it's believed they lost contact because it overflowed the unsigned 32-bit integer where they stored time, and it got stuck in a reboot loop. So there are actually countless examples of similar problems, obviously not the year 2030 problem, but happening in lots of other cases. So this is a problem, this is something to worry about, this is something that needs to be addressed. That's all the bad news. So what do? Luckily, on the good news, there is a solution kind of already agreed upon. And so the generally agreed upon solution is that we'll migrate 32-bit systems to use a 64-bit time T. This matches what 64-bit systems already do, and unlike other solutions such as using unsigned time, 64-bit time T will take a very long time to overflow, and none of us will be alive to worry about that. So Linux 5.1 actually added support for a 64-bit time T user space for 32-bit architectures. So like I just mentioned, the 5.1 kernel added support for 64-bit time T architectures. At around this time, there was no upstream support for RISC-V 32-bit. The decision was made that RISC-V would only ever support this new syscalls. And so I'm going to talk about that now. So these new syscalls added in the 5.1 kernel expose a 64-bit time T. So all the original old syscalls are backwards compatible and still there. So on most 32-bit architectures, the idea is they can continue to use these 32-bit syscalls or migrate across to using the new 64-bit ones. Eventually, everything will be using these new 64-bit syscalls, and the 32-bit syscalls can be removed, ideally before the year 2038. These new syscalls only apply to 32-bit architectures. 64-bit architectures are completely unchanged and don't even have access to them. So the idea was, and the decision was made, that RISC-V would only ever support these new ones, these new 64-bit syscalls. The advantage of that is we don't have these backwards compatible things that we have to maintain. We don't have these legacy syscalls. We also don't have to migrate. We don't have to handle a migration plan to update from using the 32-bit ones to the 64-bit ones. We only ever have one type of syscall. This, though, is pretty much what led to the Glibc port taking so long for RISC-V 32-bit. And so these are just some examples of what the syscalls look like. So as you can see, things like clock get time become clock get time 64. Clock set time is the same, while clock nanosleep became clock nanosleep underscore time 64. And wait ID fully replaced the old wait for syscall that has now been removed. So now that we've kind of talked about the decision to use only 64-bit time T and explained why it's taken so long, let's actually talk about 64-bit time T in Glibc. So when all this decision was made, there actually was an initial RISC-V port for 32-bit RISC-V. This was done by Zong and was, though not yet upstream, was kind of floating around ready to go. This kind of changed everything, switching across to a 64-bit time T, and the port had to be started again. So when the upstream effort started for this new 64-bit time T support, Glibc actually didn't have any 64-bit time T support. There were plans as far back as 2015 on discussing it and kind of an idea of implementation, but it hadn't really started. So Lucas, myself, and other Glibc contributors have been working on adding 64-bit time T support to 32-bit architectures. So Lucas is working on a migration path for current architectures such as ARMv7 so that they can be ported over to the new 64-bit time T syscalls in a backwards compatible way. This ends up actually being a lot more work than what we have to do in RISC-V world, as we don't have to do this migration path, which is luckily for us. So all the libc functions need to be updated to use this new syscalls. And this needs to be done without impacting performance on a 64-bit architectures. So Glibc is commonly used on higher, larger sized desktop applications, like for example, and we don't want to slow down every server in the world just to use these new syscalls. We also need to do this in a backwards compatible way. So we want to run the latest Glibc on the 3.20 kernel, for example, and we want to make sure that still works. The 3.20 kernel doesn't have these new syscalls, so we don't want to use them. But we also then, when running on the latest 5.8 kernel, want to make sure we use and utilize these new syscalls. And it needs to be generic. We don't want to implement every syscall in a RISC-V specific way, because then we have to maintain that, and then it's a lot of work on the RISC-V community. We also don't want to use 32-bit specific versions, because then we have to maintain that. We want to use a generic implementation. And this then allows reduced maintenance burden, reduced code duplication, and it also means it helps all other architectures, and all other architectures can benefit from this work. So to make things even harder, some kernel syscalls only support 32-bit time T. Things like getRUsage, setITimer, and getITimer. These use relative times, so the idea is they won't overflow, and if the thinking was that it would just be simpler if we just reduce or change as little syscalls as we can get away with. This doesn't really end up being the case, as everything else around it is 64-bit, so in these functions, for example, we need to convert to and from between 32 and 64-bit times. There's even some more complex cases. Things like semctl and friends return 32-bit high value. So where they used to return a 32-bit time and a reserved field, they now return a 32-bit time and a 32-bit high time. So we can bit shift across and OR it in to get a 64-bit time. This is pretty simple, but just handling all the corner cases of what if you're running on a kernel that doesn't do this? What do you have? You have to zero it out and not use them, and how do you tell that? Then running on a new kernel, and also taking into account the migration plan for other 32-bit architectures and doing this in a backwards compatible way. As well as that, the alignment changes of a lot of these structs in the syscalls, as 32 and 64-bit variables have different alignment constraints. And the wait for syscall. So the wait for syscall has been fully removed in these new 64-bit versions, and it should be fully replaced with the wait ID syscall. So Glibc will convert to and from when the user space application calls the wait for function. It'll convert that into the arguments for a wait ID kernel syscall. And the 5.1 kernel actually has a bug where the wait ID syscall cannot fully replace the wait for syscall, and I'll talk about that a little later. So this is kind of an example of what this new syscall interface looks like. So hopefully you can see my cursor on the screen. So this is the clock nanosleep function. And notice this is the time 64-bit version. So if we're assuming time 64 syscalls, like on 64-bit architectures or architectures like RISC-V, then we just go in and do the syscall. Notice that if we don't have the new time 64 syscall defined, we define it here. That's because 64-bit architectures don't have this underscore time 64 version, so we end up just calling the generic old one and just using some macros to simplify the code. So RISC-V will only ever just call this top one. On older architectures though, that don't have this assumption, we first check if we have the new architectures, if we were compiled with support for them, the new syscalls I mean. Then we'll call that syscall, and if it worked, return a success. If that doesn't work, we fall back to the old way. Notice though that we have to convert the 64-bit time we're using here to the 32-bit time to pass to the old syscall, and then convert it back at the end. So this function takes a 64-bit time in, and this is directly called on 64-bit architectures, as well as things like RISC-V. Older other 32-bit architectures will have a wrapper function around this that will convert the time to a 64-bit time. So although they have some more overhead, the idea is they'll eventually migrate away from this. So now we've kind of gone over the Y2038 problem, how it's been fixed. I'll talk about the current status of it. So Glibc 2.32, that was released about a month ago, adds support for 64-bit time T on 32-bit architectures. In fact, it actually supports one architecture, the ARC port. So the ARC port is the first port that supports 64-bit time T on 32-bit time, using all the generic work that went ahead for RISC-V. Unfortunately, the RISC-V port didn't make it in for this release, as we couldn't get enough reviewed bys on the patches to have it merged. And this is just an example of some of the converted syscalls look like. Clock at time, U-time and set, and peephole, things like that, have all been converted across. So, RISC-V support will hopefully be included in the next Glibc release, 2.33, which will come out in about 5 months. So, I mentioned earlier about the wait for bug as well in the kernel. So the RISC-V 32-bit report will require the 5.4 kernel and the 5.4 kernel headers. This is because the 5.1 to the 5.3 kernel has a bug in it related to the wait ID syscall. So for the wait ID syscall to fully replicate the wait for syscall, we need to be able to wait on the current processor's group. And the expectation was that Glibc could do this by first querying the group and then calling the wait ID on that specific group. It turns out though that this is open to race conditions where the group or the process could change between those two syscalls, and it's also wasting time calling these two syscalls. The 5.4 kernel fixed this by adding the PGID ID type for the wait ID function, and this is what we need in order to fully replicate the wait for syscall. Because of this, the RISC-V 32-bit port and all other 64-bit time T 32-bit ports will require the 5.4 kernel or newer. So it's been a fair bit of work to get here. We've converted all these other functions across. We've done not just the 32-bit RISC-V port, but all this other generic work. So was this worth it? Why bother with all this work? So partly just for completeness. The RISC-V spec supports 32 and 64-bit RISC-V and boots Linux on both. And now we can say we support that in upstream Glibc, or at least soon we'll be able to say that. And 32-bit support also improves testing. It's useful to test the kernel with 32-bit booting, It's also useful for tools around the kernel, things like toolchains, emulators such as QEMU, and build tools such as Open Embedded and BuildRoot. As a QEMU maintainer, it's very useful to do testing patches by booting 32-bit Linux as well as 64-bit Linux. It's also useful for FPGAs. So FPGAs can save a lot of space by running a 32-bit soft core instead of a 64-bit soft core. They also make it easier and cheaper to have Linux-capable FPGAs. For example, the VEX RISC-V FPGA soft core can already boot 32-bit Linux. It will now be able to do it with an upstream Glibc. And small embedded Linux systems might like to avoid the overhead of 64-bit CPU design, page table lookups, and application sizes. So what's the current 32-bit RISC-V status? There are multiple versions being submitted upstream, and some of the patches have been reviewed. As of recording, it's probably close to 50% of the patches, but more reviews are still required. I'm not going to point to the latest patch set, as by the time you watch this, that's probably out of date, but if you're interested, you can look at the Glibc mailing list and see them there. The latest patches can be found on my GitHub, unless it's already been merged into mainline Glibc, in which case it's just available there. I mentioned earlier that I'd talk about future work. Some future work will be things like improving the RISC-V 32-bit float support. At the moment we do have some basic floating point support in the 32-bit port, but that needs to be improved. The idea here in the future will be to consolidate the 32-bit and 64-bit together into one single generic RISC-V implementation, and that way we'll both be aligned. There'll be obviously some differences based on the XLens, but that can all be handled just with some macros inside the generic implementations. There's also a procedural linkage table failure that will be discussed at Plumbers next week as of time of recording, and by the time you watch this, hopefully a solution will at least be determined for that. So there's also other projects that need to be updated. So Glibc is not the only thing that will need to be fixed for this. So obviously other libcs need to be updated to 64-bit time T as well. Things like Muscle will have to go through the same amount of work. But not all applications don't do syscalls. Some do their own syscalls. Things like OpenSSL and BusyBox, for example, have already been updated to do this, but there's lots of other things. So luckily, this is a compile time failure. As they try to do these syscalls that no longer exist, they'll fail to compile. So we need to do some sort of big, large build testing to figure this out. Something like a dev bootstrap or OE world build should be able to catch a lot of the RISC-V 32-bit failures, and then we can work on sending patches upstream. Any application that does futex calls, time calls, anything like this will probably need a patch to be fixed. And on top of that, again, there's obviously even more work in other tools. Things like 32-bit Rust, user space Linux support will need to be added after this. I'm a fan of Rust, so I think that's worth doing. So the benefits that RISC-V has over other architectures with the 64-bit time T are actually quite extensive. So 32-bit RISC-V has the large benefit, and we now don't have to maintain these backwards compatible 32-bit interfaces anymore. We can just use these single new 64-bit interfaces. We don't have to worry about year 2038 problems, and we don't have to worry about migration plans. So that's all very helpful. RISC-V also uses generic syscalls. So that means we don't have to have specific RISC-V versions, and the RISC-V Glibc port for both 32 and 64-bit is actually quite small. This reduces maintainer burden, as we don't have to handle these other syscall interfaces. There are unfortunately some mistakes in the original RISC-V port though. The two big ones that kind of stand out is that the word size times 64 compat32 macro was defined as 1. So that might seem confusing, but basically what it means is that we told Glibc that we expect the time to be 32-bit for RISC-V 32-bit. And this is used for things like the login syscall, the getRU line syscall, and things like that. This unfortunately means that 64-bit RISC-V has been using 32-bit values for these, and that 32-bit RISC-V will also have to use 32-bit values in order to maintain compatibility between the two running on the same system. This was done at the time with the assumption that 32-bit RISC-V would use the 32-bit time T, which seemed likely at the time, but is no longer the case. We can't just turn this off, as that will break backwards compatibility. So this is something that now needs to be migrated for both 32 and 64-bit RISC-V. Not ideal, but something that can be worked around. There's also this struct, this pthread rw lock arc struct, The RISC-V 64-bit version uses a non-generic version. It has an architecture-specific one, while the RISC-V 32-bit uses a generic one. So again, it's not the end of the world, but it just means that we have to maintain these two different structs now. So lessons, my final slide, some lessons learned from upstreaming. So Glibc upstreaming is a very slow process. This process has been going on for over a year now, and before that there was already a mostly working 32-bit RISC-V port floating around anyway. So the reason is because changing core functions in Glibc requires lots of testing. There's a scripts build many Glibc's Python tests that's very helpful for smoke testing. It'll build and run smoke tests for every architecture, but this can take a long time to run. It takes up to 12 hours. On top of that, checking backwards compatibility for 32-bit architectures is even harder. At one point, I was testing changes for 32-bit ARM and testing with the 4.19 kernel and the 4.19 headers, the 5.1 kernel and the 4.19 headers, and the 5.1 kernel and 5.1 headers. So this is a whole range of different combinations of with and without the new 64-bit syscalls to make sure we didn't break any other architectures. You also have to run full tests on 32-bit QEMU for RISC-V, and it takes about 19 hours to run from a clean build and test. So it takes a long time to make a change and test it all before submitting new patches. And thinking about how these changes affects every other architecture also slows down work. At one point I was making changes to the DEC Alpha architecture. I don't even know how to get access to one of those machines to test it, but you still have to try and make sure you don't break anything and don't affect performance in these architectures. But in saying that, the Glibc community is very friendly and very good at responding to patches and very happy to help. So that has made the process a lot easier. So that's the end of my talk. I hopefully will be able to call in right now and answer any questions in person. If that doesn't work, I should just be able to answer the questions in the text chat as well. So thanks for listening.